Welcome to another AQA's chemistry video, and today I'm going to be doing a video on trends of ionization and specific impacts of ionization energies. So let's start to the first part of the video, trends of ionization. So first, ionization energies change in a predictable way throughout the periodic table. The trend down the group is the first ionization energy decreases down the group. So as you go down the group, the first ionization would decrease. The reason for this is that the atomic radius would increase, so the electron is further from the nucleus and so it experiences a lower attraction. What I mean by this is that you're removing an electron from, if you remember we were talking about higher quantum number, you're removing an electron. As you go down the group, you're gaining the number of as you go down the group, the number of electrons in the outermost shell stays the same, but you now have one extra electron shell. So as you go down the group, just in general, just if you're talking about the periodic table in general, forget the periodic table out right in here, right? There's the same number of electrons in the outermost shell, but now there's an extra electron shell. So one electron in the outermost shell, but now there's only 2 electrons in lithium. Whereas if you go down to sodium, there's 3. It's 3, 4, 5, 6. You get the point. So you're getting an extra electron shell more. So when you're going from down the group, the reason why the ionization energy would decrease is because you're removing an electron from another electron shell that's further away from the nucleus, and therefore less energy is required to remove that electron. So also more, on top of that, there are also more electrons between the nucleus and the outermost electron. Therefore, the outer electron experiences greater shielding from the nucleus, like I said before in the previous video, also providing evidence for the existence of shells. Right, the trend across the period. The first ionization energy increased across the period. So as you go across the period, so down the group, remember you're gaining an electron. You're removing an electron from another shell because you're gaining a shell. If you're going down the group, as I said before, you're gaining another shell. It increases by 1 shell. The number of electrons would stay the same. The number of electrons on outermost cells are the same. The nuclear charge increases as you go down the group, but the nuclear charge increasing, it has a certain. Remember, nuclear charge. When we're talking about nuclear charge increasing, we're talking about that electrostatic attraction. The electrostatic attraction, that's that kind of feeling, that pulling factor that's keeping the electrons in place, that strong attraction, is weaker when you get another electron shell away. And that's what happens when you're increasing that electron shell. The nuclear charge is increasing, yes, but when you're adding another electron shell, it's overall a weaker attraction. However, when you're going across a period, you're adding an electron, you're removing an electron. First of all, it's in the same shell. All these electrons are in the same. When you're going across the period, they're all in the same electron shell in terms of they're all in energy level 3 or quantum number 3. And though the proton, because of that reason, now it matters that the nuclear charge is increased. So as nuclear charge, the reason why the ionization energy would increase as you're going across the group, because the nuclear charge is increasing for electrons that are being added to the same shell. Therefore, there's a stronger electrostatic attraction between the nucleus and the electron, the outermost electron, which will all be in the same. Which, in terms of the outermost electrons, will all be in the same. If we're talking about from the third period, the third shell. So therefore, when you're talking about periods, or we're talking about ionization energy, when you're talking periods, it would increase as you go across the period, because the electrostatic attraction between because if you're answering it as for example, as an exam question, you would say ionization energies increase as you go across a period because the nuclear charge increases. Therefore, the electrostatic attraction between the nucleus and the outermost electron is higher. Therefore, more energy is required to remove that electron. So, enough me rambling about this now. The first ionization energy increases across a period because the atomic radius decrease, right? So when that electrostatic attraction would increase, that causes the radius or electrons to move closer to the nucleus, and that would decrease the atomic radius. So if you were to imagine the size of atoms as you go across the period, that actually individually gets smaller and smaller and smaller and smaller because the nuclear charge is increasing and electrons are in the same shell. Therefore, the atomic radius would decrease, high electrostatic attraction, electrons are closer to the nucleus, more energy required to remove an electron, right? Because the atomic radius decreases, proton number increases across a period, so electrons are more attracted to the nucleus. The electron is close to the nucleus and so experiences a greater attraction, and the nuclear charge increases across a period. Great. Now on to the next part of the session is specific impacts of ionization energies, right? Impact of subshell structures on ionization energy. So the impact of subshell structures is enough to sometimes outweigh and contrast general trends in ionization energy. So in this part of the video, I'm going to explain that. So this is the general trend, right? What I said before is the general trend when you talk about ionization energy is going down the group, ionization energy decreases. Going across the period, ionization energy increases, right? And there's some, I'm going to go through what, there's some things that don't generally, it kind of goes against the rule. Generally, this is the rule that we follow, but there's some instances that you actually need to know in the exam where it doesn't follow it, and there's a reason for why it doesn't follow it. And it's kind of relating to what I talked about in the previous video about electron shells and orbitals. But I'll get onto it now. So, example of subshell impact, right? So this is the, they usually like to do period 3, but I've seen them also use period 2 as well. But the same, don't get confused saying, it's a different thing. It's the same idea if they use period 2 or period 3. But I'm using period 3, right? An example of subcellular structures is the difference in ionization energies between magnesium and aluminium within period 3. They're in the same period, and so we would expect aluminium's ionization energy to be greater due to the greater nuclear charge. However, this is one of the contrasts of the trend. So we're expecting aluminium to have a higher ionization energy compared to magnesium, right? Because it's in the same period and it's more further across in the period, so it has a higher nuclear charge. We're expecting aluminium to have a higher ionization energy, right? Therefore, however, contrast to the trend, the ionization energies, don't mind the typo, are for magnesium 738 and aluminium 578. So magnesium is much higher than aluminium. So this breaks the trend. This is not what we would expect. The reason for this are these values don't align obviously with the general trend that we predicted, and we need to look further in subshell structures of these atoms to understand what's going on. The reason for this is to do with the orbitals, right? So if we're talking about the electronic configuration, when we're talking about magnesium, magnesium's electronic configuration is 1s2, 2s2, 2p6, 3s2. So the first ionization energy first ionization would remove an electron from the 3s orbital, whereas in aluminium, the first ionization energy removes an electron from the 3p orbital, right? And if we're talking about subshell energies, the 3p orbital is further from the nucleus on average compared to the 3s orbital. So this orbital has a higher energy and its electrons have a lower electrostatic attraction to the positive nucleus. Remember what we talked about in the previous video when we did the little pyramid that I did, right, with the arrows going this way and this way and this way. So a 3p orbital generally, I did show you in the previous example in the previous video. I guess should I leave a link in the description? I mean, it's just literally the last video, so but I'll still leave a link in the description anyway. But yeah, the p orbitals, s orbitals usually are the lowest energy orbital, then followed by p, d, and then f, right? So in this example, p orbitals have a higher energy because they're further away from a nucleus on average at least, compared to they're in the same shell because they're still both quantum number 3, but p tends to be slightly further away on average from the nucleus compared to the s orbital, and therefore it regards as the electrons have more kinetic energy. They can move around a bit more freely compared to s orbitals. Because of that, less energy is needed to actually remove the electron. Because if we're imagining the ionization energy as an, if we're imagining ionization energy, right, as like an activation energy, right? Imagine the s orbital being like this. Imagine this being the activation energy, which is the ionization energy. The ionization energy is a kind of activation energy of sorts, right? The s orbital is like here, and the p orbital, the free s2 orbital is here, and the free p orbital is here. So this is what it means. A higher energy orbital, therefore less energy is required for it to reach this ionization energy in order to remove an electron from the free p orbital compared to the free s orbital, and therefore more energy is required to. That's why the ionization energy of aluminium is less than the ionization energy of magnesium, and this is one of two examples that you need to know for where the trend is. This doesn't follow the general trend of, as you go across the period, ionization energy would increase. On top of that, on top of this as well, there's also the slight fact that in aluminium, the 3s2 orbital kind of acts as electron shielding. It kind of shields the 3s2 orbital, shields the 3p orbital from the nucleus as well. So that's a little small thing as well, but generally what I was talking about here with the orbitals though. All right. Therefore, it's easier to ionize an electron in the 3p orbital than the 3s orbital. This explains why it's easier to ionize aluminium than magnesium. Sorry for all the typos, I should have looked at this before. This outweighs the general trend we looked at first. And evidence for these arguments, we can use the relative phase ionization energy value of magnesium and aluminium as evidence for subshell structures. So this is actually evidence to say that there are subshell structures, not just shells of 1, 2, like you would in GCSE, was the first shell, the second shell. This is proof that there are subshells. There's meaning behind why is the ionization energy so different, right? But all right, let's just move on now. The impact of electron repulsion on ionization energies. So there's a second example, right? That was the first example of when the trend, it doesn't really follow the trend. This is the second example. So the impact of repulsion on ionization energy. So the impact of repulsion can be seen in the ionization energies of group 5 and group 6, phosphor and sulfur. Both phosphorus and sulfur have their outer electron in the 3p orbital. So they're both electrons in the 3p orbital, right? Phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3, and sulfur is the same but it's 3p4 instead. So 1s2, 2s2, 2p6, 3s2, and 3p4. The shielding for each atom's outer electron is identical. It's not like the previous one wherein aluminium it's slightly shielded by the 3s orbital. They're both in the same suborbital here, so that's not a problem. But S has a higher nuclear charge. Sulfur has a higher nuclear charge. So you would expect, given that it has a higher nuclear charge, the S to have the higher ionization energy. However, this isn't the case, because there's something to do with simply or doubly occupied orbitals. So I shouldn't say simply, I should say singly. I was about to say singly. There's way too many typos in this. Yeah, right. Singly and doubly occupied orbitals, right? So with the phosphorus electron is removed from a singly occupied orbital. If I was just to do the 3p orbital, this, right? This is what the 3p orbital would look at on phosphorus. Whereas in sulfur, it looks like this. I'm just talking about just the 3p orbital, right? I could do the rest, but they're all full. Now this is where the problem is now. So I'll say a problem, but S is a high ionization energy because the electrons in the same, sorry, the phosphorus electron is removed from a singly occupied orbital, but in sulfur the electron is removed from a doubly occupied orbital. Sulfur has a high ionization energy because the electrons in the same orbital repel each other. That's the part you need to realize here. The electrons in the same orbital repel each other, meaning that an electron is easier to remove from a doubly occupied orbital. So these two electrons here would actually repel each other, and because of that, that repulsion there actually prevents that strong attraction to the nucleus, and that's what's causing. That is partly the reason why it's so easy to, or less energy is required to remove an electron from a doubly occupied orbital, because of that electron repulsion, because these electrons in this orbital here are double, or as in a pair, less energy is required to remove this electron because of that repulsion, which would prevent that strong attraction to the nucleus, compared to with phosphorus, they're all single. There's no electron to cause in a pair to cause repulsion. So giving this furthermore always gives more evidence for the electronic structure model that we've currently been using. So if it's to sum up this entire video, the first ionization energies for magnesium and if I was to just do the first one there, first ionization energy of magnesium and aluminium and let's have an aluminium here. Right, so we already know with this here, we're just talking about the orbitals. Because this is the same, 1s2, 2s2, 2p6, and then 3s2 and 3p1. So here you're removing an electron from, I'm not going to write any more, you're removing an electron from the 3p orbital, whereas with magnesium, you're removing an electron from the 3s orbital. And the first ionization energy for magnesium is 738 kilojoules per mole. Don't have to know this, but just to show you that there's a significant difference in the first ionization energy. First ionization energy for aluminium is 578 kilojoules per mole. And if we now to compare first ionization energy of phosphorus and sulfur, right? We're talking about phosphorus, sulfur. It's about 1s2, 2s2, 2p6, 3s2, 3p3, and so 3p4 here, right? And that's the part that matters. 1s2, 2s2, 2p6, 3s2. But at the end of the day, this is the only part that really matters here. And that's a singly occupied orbital. and a fuck's sake, doubly occupied orbital. And that because of that electron repulsion, I don't know why I did a massive. This is a singly occupied orbital, whereas in sulfur there is a doubly occupied orbital. This electron repulsion here, that's what causes there to be a weaker electrostatic attraction. That repulsion would make it easier or less energy is required to remove an electron from the outermost, to ionize or remove an electron from the outermost from sulfur atom. And as you can see it. Have I got the data for that? I haven't. I don't think I had. Did I write it down? I must have not written it down. But it is lower. It is lower. Like if you go to the, actually I could probably go to. Actually, I probably could just go to. Yeah, there you go. Right. Periodic table is a website you can just go on about. It has to compare phosphorus's first ionization energy, 1111.8, whereas sulfur should be less, 999.6. And therefore there is. Thanks for watching this video. Hopefully it was helpful. That's it.